Welcome to our video about UV-Vis spectroscopy, a powerful analytical technique that allows us to gain deeper insights into the unique traits and attributes of molecules. UV-Vis spectroscopy is a non-destructive, quick and cost-effective method that provides valuable insights into the composition of substances. In this video, we will delve deeper into its principles and practical applications. First, let's talk about the electromagnetic spectrum. The UV-Vis spectrophotometer uses optics to analyze the sample. It begins with one or two light sources that emit UV, visible and near-infrared light. These wavelengths can be seen on this spectrum, and they range approximately from 100 nanometers to 1000 nanometers. As we know, the human eye is only capable of seeing around 380 to 700 nanometers, and this is what we call visible light. This technique allows us to easily measure samples that absorb light in this wavelength range. To understand UV-Vis spectroscopy, let's first grasp the fundamental principles. When ultraviolet and visible light interact with atoms and molecules, it can cause electrons to jump to higher energy levels. This happens when an atom absorbs a photon with energy high enough to excite one of the electrons to a higher energy level. Let's look at an example of a lithium atom. We see the electron absorbing a photon, which then jumps to a higher energy level. This is the excited state. At some point, the electron will emit the photon and return to its initial position. Again, the photon has the amount of energy that is required to make the transition. This also happens to molecules. Let's take a look at the conjugated molecule 1,3-butadiene, which has 4 pi electrons occupying the atomic orbitals. Initially, all of the electrons are in their ground state, which is in this case in the bonding molecular orbitals. Let us note the highest occupied molecular orbital, or the HOMO, and the lowest unoccupied molecular orbital, the LUMO. When absorbing a photon, one electron will move into the anti-bonding molecular orbital, or the LUMO. The transition requires a photon to have the energy of at least delta E, which is indicated here. As such, this technique can provide insight into the energy difference between occupied and unoccupied energy levels. The instrument detects transitions based on light intensity and converts them into valuable data. Typically, the UV-Vis spectroscopy results are presented in an absorption graph that is shown in the following image. When you obtain a UV-Vis spectrum, you'll see peaks and patterns. These represent the absorption characteristics of your sample at different wavelengths. You can calculate the energy of absorbed light with the following formula that is derived as shown. Now, more about the instrument itself. The UV-Vis spectrometer is usually quite bulky and looks as such. As stated earlier, there are 1 or 2 light sources that emit UV, visible and near-infrared light. Mirrors guide this light through a monochromator, which selects a variable wavelength, allowing us to measure the entire spectrum from 190 nanometers to 800 nanometers. Next, the monochromatic light passes through the sample and reaches a detector, which measures the intensity of the transmitted light. This information is crucial for our analysis. The accuracy of the measurements can be changed in the software, but more accurate measurements also take longer to perform. Now, let's talk about the Beer-Lambert law, a fundamental equation in spectroscopy and UV-Vis spectroscopy in particular. For molecules in solution, it relates absorbance to molar absorptivity, path length, and concentration. The following parts of the equation show the relationships between absorbance, Beer-Lambert's law, the light intensity is measured in the instrument, and transmittance. By understanding this law, we can determine the concentration of a solution if the extinction coefficient is known. Vice versa. From a known concentration of an unknown compound, the extinction coefficient can be determined. This can tell us the specifics of the material at different wavelengths, by which we can confirm the material's composition or find out what the composition is based on some known absorbances. Keep in mind, if absorbance exceeds 1, we should dilute the solution to ensure accuracy. Sample preparation is crucial for accurate UV-Vis spectroscopy. Bear in mind that transmission is actually measured, so samples should not be too optically dense. For solution, a concentration of 10 to the power negative 4 molar is a good starting point. Measurements are done in comparison with a blank sample to correct for the absorption of the cuvette and solvent in case of solutions or substrate in case of thin film. These measurements are done sequentially in a single beam spectrometer or side by side in a more advanced double beam spectrometer. Now, using the instrument. First, we prepare a blank sample, so only the solvent. In our case, isopropanol was used. We wipe the sides of the cuvette to remove any residue and place the cuvette inside of the slot. Make sure that the clear side faces towards the beam of light coming from the machine. We then close the lid and go to the computer. At first, we need to calibrate the machine with regard to the blank sample. For that, head on over to the correction page and make sure this box here is ticked. Then, head back to the first page and click on Start. This will automatically start the Auto Zero, but you can always Auto Zero with a corresponding button as well. We then open the lid, remove the blank sample and insert our own sample. Again, wipe the sides and keep the clear side towards the beam. We then press Start again on our computer and start measuring the sample. The graph obtained looks like this. Save this file to the computer and transfer it to your own device. To measure thin films, switch out the cuvette holder and follow the same process. First, we Auto Zero with respect to just the substrate. Place your substrate into the instrument and Auto Zero. Then we take out the reference and place in our sample. Make sure to wear gloves if working with toxic materials. Place your sample into the holder. Then we close the lid and start measuring. The process is almost the same, and we ended up with a graph that looks like this. Now, let's dive into the results. On the left side we see sample 1, which is fast green FCF, which is a food coloring compound. On the right we see sample 2, which is a perovskite material used in photovoltaics. When you obtain a UV-Vis spectrum, you'll see peaks and patterns. These represent the absorption characteristics of your sample at different wavelengths. You can calculate the energy of absorbed light with a previously derived formula. To analyze, identify peaks and use the Beer-Lambert law to determine concentrations. From the first sample, we can clearly see a peak at 614 nanometers. This data can reveal the composition of materials or help confirm known substances. Keep in mind, the visible color of a compound is the opposite of the absorbed color in the color wheel. Sample 1 absorbs orange light at 614 nanometers and it appears blue to us, which is in line with the color wheel. Sample 2 absorbs blue and green light, which is why it appears red or orange to us. UV-Vis spectroscopy finds applications in various fields. For instance, it is used to measure caffeine levels in commercially sold drinks, ensuring product quality and safety. UV-Vis spectrometers are also widely used in the medical sciences for the analysis of blood and urine samples. In addition, this technique is also ideal for analyzing reaction kinetics when the change in reactant or product produces a change in absorbance at a specific wavelength over time. Always contact the lab supervisor when having issues with the instrument. Thank you for watching and good luck in the lab.